On January 16, 1943, the SS Schenectady rested quietly at dock in Portland, Oregon. She was a brand new Liberty ship, barely 10 weeks old, fresh from the Kaiser Shipyards. No enemy fire threatened her. No storm tested her hull. The morning was calm, the water still. Then, without warning, a single sharp crack echoed across the harbor. Within seconds, the entire ship split in two, the hull torn from deck to keel, as if sliced by an unseen hand. Sailors scrambled as the bow and stern sagged in opposite directions, the ship's back broken, while still tied to the pier. The Schenectady wasn't alone. That same winter, the SS John P. Gaines snapped apart in quiet seas. The SS Manhattan, a T-2 tanker built the same way, cracked so violently her crew abandoned her in fear. Between 1943 and 1944, more than 2,500 Liberty ships reported serious structural failures. Hull fissures, deck ruptures, catastrophic splits. At least 19 ships broke clean in half. 3 simply vanished at sea, disintegrating so quickly they never sent distress calls. These weren't war losses. These were ships destroying themselves. The United States had wagered everything on the Liberty ship program. After Pearl Harbor plunged America into total war, the nation desperately needed cargo vessels, hundreds, fast. Traditional construction took 8 months per ship. The Maritime Commission couldn't wait. Industrialist Henry Kaiser, who had never built ships before, made a daring promise. Mass-produced freighters assembled like automobiles, completed in weeks instead of months. His Richmond, California yards pioneered new methods, welding instead of riveting, prefabricated sections instead of slow hand assembly, and borrowed Detroit's assembly line discipline. By late 1942, Kaiser's yards were turning out Liberty ships in an average of just 42 days. The propaganda machine hailed it as an industrial triumph. Newsreels showed Rosie the Riveter, though now they were welders, transforming raw steel into ocean-going giants at impossible speed. The SS Robert E. Peary set the ultimate record that November, built in only 4 days and 15 hours from keel laying to launch. America cheered. Allied tonnage lost to U-boat wolfpacks finally had replacements flooding the Atlantic. Then the ships began breaking. Not from torpedoes or tempests, but spontaneously, catastrophically, in calm conditions. Engineers were stunned. The welds appeared perfect. The steel met standards. The blueprints were proven British designs, yet Liberty ships were fracturing like glass. Cracks often began at sharp corners, hatch openings, and gun mounts. Mounts, the squared-off contours of the hull, these became the origins of disaster. Once a crack began, it raced through the welded plates at terrifying speed, sometimes traversing the full length of the ship in seconds. The Maritime Commission launched urgent investigations. Metallurgists studied fractured hulls under microscopes. Engineers recalculated stress loads. Naval inspectors crawled through twisted steel with gauges and notebooks. Everyone was hunting the cause. Bad steel, faulty welds, flawed designs, or lax quality control. Yet while committees debated, ships kept breaking. Sailors grew afraid of their own decks, knowing the hull beneath their boots might split open without warning in the freezing Atlantic. The miracle of mass production had turned into a maritime nightmare, and no one could explain why ships built so swiftly were dying just as fast. The breakthrough came from an unexpected source. A welder on the night shift who wasn't supposed to question the engineers. Bessie Hamill worked at Kaiser's Richmond Yard, No. 3, one of thousands of women who had taken up industrial jobs after the men went to war. For 8 months, she'd been welding hull plates long, enough to notice something strange. The welding sequence made no mechanical sense. Night after night, she watched her crew start welds at the edges of the plates or run long, unbroken seams from one end to the other. Each weld cooled and contracted, warping the plates and building stress she could see forming in the glowing metal. When welders finished one panel and began the next, they were locking that stress inside forever, like tightening the center bolts on a wheel before the outer ones, guaranteeing imbalance and eventual failure. Her foreman brushed her off. She was a welder, not an engineer. The sequence came from men with naval architecture degrees, not from the shop floor. But Hamill wouldn't let it go. In November 1943, she broke chain of command and asked for a meeting with yard supervisors, a move that could have cost her job. She brought test plates she'd welded on her own time, each using a different sequence. Some were visibly warped and twisted. Others, welded from the center outward in a balanced pattern, lay perfectly flat with almost no distortion. Skeptical but curious, one supervisor observed her team in action. What he saw confirmed everything. The welding order was effectively torturing the steel, trapping massive residual stresses in the structure. Every seam added invisible tension that concentrated at sharp corners and hatch edges, the exact spots where ships were failing. When Liberty ships hit the frigid North Atlantic, the steel turned brittle. Those locked-in stresses combined with the cold to create perfect conditions for catastrophic fractures. Hamill's solution was brilliantly simple. Weld from the center outward so tension could dissipate toward the edges. Alternate welding positions to spread heat evenly. Never complete long continuous seams. Instead use short balanced welds that allowed the metal to cool evenly. It wasn't a grand theory from textbooks, just practical wisdom from someone who felt the steel shift beneath her torch. By December 1943, her findings reached Henry Kaiser himself. He faced a hard choice. The Liberty program was already under political fire for its cracking epidemic. Admitting that the problem came from construction sequence, not steel quality or welding chemistry, meant every ship built so far carried a hidden flaw. Fixing it would require halting production, retraining welders, and reworking the entire assembly process. But it might also save the fleet. To his credit, Kaiser acted immediately. He ordered full-scale tests of Hamill's method, dedicating an entire hull section for controlled reconstruction. The results were shocking. When metallurgists compared conventionally welded panels to those built using Hamill's sequence, the difference was undeniable. Stress gauges showed the old method created internal tensions exceeding 30,000 pounds per square inch at key joints, while Hamill's approach reduced peaks to around 12,000 psi. The steel was the same. The welds were chemically identical, only the order of operations had changed. Yet the structural strength had improved dramatically, factors the engineers initially refused to accept. But now the physics behind the failures became unmistakably clear. Steel is not a static substance, it's a crystalline structure that reacts dynamically to heat and cold. When welders run a torch along a seam, they create a narrow zone exceeding 2,500 degrees Oz. The metal there expands intensely, but as it cools, it contracts. The surrounding cold steel resists that contraction, trapping immense tensile stress unless the welding order allows it to spread out. The Liberty ships were victims of what metallurgists call brittle fracture propagation. The steel used in their hulls, a carbon-based shipbuilding grade, behaved well in warm waters, but underwent a critical shift in near-freezing Atlantic temperatures. Below roughly 40 degrees, the metal's ductility collapsed. Normally, steel absorbs stress by flexing slightly, bending instead of snapping. But cold robbed it of that flexibility, making it behave more like glass than the tough alloy welders handled under California's mild skies when brittle steel met concentrated. Residual stress at a sharp corner, like a square cargo hatch edge, physics acted with merciless precision. A microscopic crack would form. In ductile steel, it would stop, absorbed by the material's ability to yield. But in brittle steel under tension, the crack became a sprinting fracture. The energy stored in those locked-in stresses fueled it forward. Sharp corners acted as multipliers, amplifying local stress by threefold or more. The crack would accelerate, sometimes faster than the speed of sound, tearing through the hull before any frame or bulkhead could halt it. The SS Schenectady's disaster made perfect sense in retrospect. Built in winter using weld sequences that maximized internal stress, her hull carried millions of pounds of hidden tension. When the temperature in Portland fell to 28 degrees, the steel turned brittle. Stress at a hatch corner triggered a crack that found an uninterrupted path through continuously welded plates. No riveted seams to slow it, no stress relief points to interrupt it. The ship tore apart in seconds, releasing years of stored energy in one violent failure. Traditional riveted ships hadn't suffered this fate, and the reason revealed why welding, for all its speed, was inherently risky. Riveted construction is naturally discontinuous. Each plate is an independent element. A crack that begins in one plate stops cold at the riveted joint. The overlapping plates and mechanical fasteners act as natural barriers. Welded ships, however, are continuous. A crack in one panel can run unbroken through hundreds of feet of seams. The same efficiency that made welded ships faster and cheaper also made them dangerously vulnerable. The Liberty ship's squared-off design made matters worse. British naval architects had chosen hard corners to simplify cargo handling. No one realized that sharp internal angles create massive stress concentrations, multiplying normal loads to destructive levels. Each wave that flexed the hull sent pulses of stress into those corners. Combined with residual weld tension and cold brittleness, those areas became ticking fracture points, waiting for the perfect conditions to fail catastrophically. Henry Kaiser understood the implications immediately. In January 1944, he faced the greatest gamble of his career and perhaps of the entire wartime shipbuilding program. He ordered a complete halt to Liberty ship production at Richmond, Yard Number 2, and diverted his resources toward a new vessel, the Victory ship. This wasn't a patch or a tweak. It was a total redesign built upon Bessie Hamill's welding discoveries and the hard-earned lessons etched into the shattered hulls of the Liberty fleet. The risk was staggering. The Allies still needed every ship they could get. German U-boats had already sunk more than 2,000 merchant vessels since 1939. The upcoming invasion of Europe, still months away, would demand the largest logistics operation in history. Every cargo ship mattered. Yet Kaiser was betting everything that he could retrain thousands of welders, re-engineer the hull design, and refine the steel itself, all while keeping his legendary production speed intact. His rivals called him reckless. Congress prepared to pounce if he failed. But Kaiser's team went straight to the root of the problem. Every sharp edge in the Liberty design was replaced with rounded transitions. Hatch openings, the birthplaces of so many deadly cracks, were reshaped with wide radii to diffuse stress. Deck and hull thicknesses were recalculated, not to add brute strength, but to distribute loads more evenly across weld sequences. Internal frames were repositioned to align with natural stress relief points, working with the welds rather than against them. The steel itself evolved. Kaiser's metallurgists specified a new alloy with greater low-temperature toughness. They reduced carbon slightly, increased manganese, and added small amounts of nickel, expensive but essential for resilience in freezing seas. Rationed for armor plating, nickel was scarce, but tests proved that adding just 0.25% nickel to the alloy dramatically increased the steel's resistance to brittle fracture. The Maritime Commission balked at the added expense until Kaiser presented the math. Saving even one ship would offset the cost of upgrading steel for 50 others. By March 1944, the new specification was approved. Then came the monumental challenge, retraining the entire workforce. By early 1944, Richmond's shipyards employed over 90,000 men and women, thousands of them welders, trained in crash courses lasting only weeks. They knew how to lay fast, clean beads, but now they needed to master sequencing, stress management, and thermal control. Kaiser opened welding schools right inside the yards, pulling seasoned welders like Bessie Hamill off production lines to teach. Each welder received a numbered sequence card for every hull section. Weld number 1 here, number 2 there. No improvisation allowed. Prefabrication expanded dramatically. Instead of welding massive hull segments on the ways, where sequencing was chaotic and difficult to control, Kaiser's engineers divided Victory ships into smaller, modular assemblies built in specialized shops. A single bow section might contain 50 individual subassemblies, each welded under tightly controlled conditions, following precise sequences, then heat-treated in stress-relief ovens before joining the main hull. This modular method meant welders could always start from the center of each section and move outward, just as Hamill had demonstrated, without being constrained by the full ship's geometry. Skeptics pounced when the first victory ships. Keel was laid in February 1944. Construction took 18 days, slower than Liberty ship records. Kaiser's yards weren't producing miracles anymore, just consistency. The second victory ship took 16 days. Critics called it proof that speed and quality were incompatible. Kaiser ignored them. He focused not on launch speed, but on crack inspection reports. The first two victory ships showed 0 structural fractures after completion, not fewer cracks, none at all. By April 1944, Richmond Yard No. 2 had evolved into something unrecognizable, a symphony of fire, steel, and precision that would have seemed impossible just 2 years earlier. It no longer resembled a shipyard at all, but a vast industrial ballet. Prefabrication zones fed into a central assembly line where hulls took form with machine-like regularity. Kaiser had effectively adapted Henry Ford's moving assembly line for ships, except instead of products moving down a line, specialized teams rotated through fixed stations at scheduled intervals. Production began in massive prefabrication sheds, where welders worked on hull sections no larger than 30 feet across. Each section had its own sequence card. A bottom plate assembly might require 47 individual welds, each numbered and color-coded. Welders began at point 1, always the geometric center, and spiraled outward in precisely mapped patterns. Supervisors patrolled the floors with checklists, ensuring no one skipped steps. After every 10 welds, the section entered a furnace heated to 200 degrees for controlled cooling. This annealing process relaxed the crystalline lattice of the steel, bleeding off residual stress before it could accumulate to dangerous levels. Meanwhile, the steel itself arrived pre-cut and pre-shaped from rolling mills that had been retooled specifically for victory ship production. Unlike Liberty ships, where plates were measured and cut on site, victory components came factory-ready. Bow sections arrived pre-curved. Deck plates were drilled with alignment holes. Frame assemblies were pre-welded and standardized. By moving this preparation to factory conditions, Kaiser eliminated variability and ensured interchangeability across thousands of parts. Assembly on the building ways followed a completely new rhythm. Rather than starting from a keel and stacking upward, victory ships were built in massive parallel modules, cargo holds, engine rooms, bows, and sterns, all constructed simultaneously, then lifted into position by colossal gantry cranes. On May 12, 1944, Yard No. 2 executed its boldest test yet. 17 completed modules, representing 85% of a full ship, were aligned and joined in just 11 hours. Welders connected the modules using Hamill's center-outward sequence. But now they were joining pre-stress-relieved sections instead of welding raw steel. The legendary 5-day build time was achieved not through shortcuts, but through absolute coordination. Night shifts pre-positioned every component. Dedicated alignment crews checked joints before welding began. Mobile cranes operated on strict 5-minute delivery cycles. Welders rotated in 30-minute bursts, followed by 10-minute breaks, a rhythm designed to sustain precision and reduce fatigue-induced mistakes. Kaiser implemented what he called the critical path method, identifying bottlenecks and redistributing manpower dynamically. If framing surged ahead while pipe fitting lagged, workers were reassigned instantly. Every task, every torch, every minute was tracked, optimized, and synchronized in real time, turning chaotic wartime production into one of the most efficient industrial systems the world had ever seen. Maintaining coordination across every construction phase. Each delay and schedule deviation was logged and studied. Morning briefings reviewed prior results, finding fixes before small errors became costly setbacks. The milestone arrived on June 27, 1944. The SS Benjamin Warner, Victory Ship Hull No. 23, went from keel laying to sea trials in just 5 days and 11 hours. Not a stripped-down demo ship, but a fully outfitted, battle-ready cargo vessel with defensive guns, complete electrical systems, a functional engine room, and every weld executed under strict stress relief rules. She showed no hull cracks. Post-construction stress readings stayed well within safety limits. On her trial run, the Warner performed flawlessly under conditions that would have fractured early Liberty ships. The 5-day Victory ship was more than a record. It marked a revolution in industrial production, where engineering discipline finally merged with hands-on practicality. Bessie Hamill's insight had triggered a complete redesign of wartime shipbuilding. The Victory ships emerging from Kaiser's optimized yards were fundamentally different from their Liberty predecessors. To casual eyes, they looked similar, standard cargo haulers, but the differences began at the molecular level, influencing every aspect of design and construction. Liberty ships had been emergency stopgaps. Victory ships were engineered solutions, built to eliminate the deadly flaws that had doomed sailors on brittle Liberty hulls. The upgraded steel formula was key. Known as killed steel, treated with aluminum to remove oxygen, it displayed vastly superior low-temperature toughness. Tests proved the ductile to brittle transition temperature dropped from about 40 degrees in Liberty steel to just 5 degrees. That 35-degree margin meant Victory ships stayed flexible in icy seas that had shattered earlier vessels. The cost increase of 8% per ton was negligible compared to the leap in durability. Even the smallest structural details embodied lessons in stress control and crack resistance. Rounded hatch corners, which seemed cosmetic, cut local stress by over 60%. Sharp 90-degree corners on Liberty ships amplified stresses up to 4-fold, while Victory ships' smooth radii kept stress multipliers below 2. In real-world terms, waves that would start a hull. Fracture in a Liberty ship merely flexed a Victory hull safely. Within its elastic range, Victory. Ships also featured crack arresters, riveted. Seemed strategically placed to break up continuous weld runs. These deliberate discontinuities acted as shock absorbers, sapping energy from any growing crack and halting its spread. It was defensive engineering, built on the premise that failure could occur, but need not be fatal. Critical structural frames were doubled, introducing redundant load paths. If one frame cracked, its twin carried the stress until repairs were made. Liberty ships lacked such redundancy. One fracture could cascade through the hull, leading to catastrophic breakup. Victory ships could take severe damage, stay afloat, and limp home under their own power. Hamill's welding innovations became codified in comprehensive technical manuals detailing every sequence pass and heat interval. Welders were trained to monitor interpass temperature. If metal exceeded 400 degrees, they halted work until it cooled. Naturally, this eliminated the distortion seen in Liberty ships, where overworked weld seams baked the steel into warped, tension-filled shapes. Quality control was relentless. Each weld underwent magnetic particle inspection, using iron filings and magnetic fields to expose invisible surface cracks. Ultrasonic testing confirmed internal weld soundness, while X-ray imaging verified full penetration and documented results for records. No ship launched without full certification. Early on, nearly 15% of welds failed inspection, but by mid-1944, rejection rates had plummeted as crews mastered the new precision. Rates had fallen below 3%. Proof of both the training program's success and the precision of the new methods. The evidence came not in theory but in service. Between June 1944 and the war's end in August 1945, 531 Victory ships entered operation, and not one suffered catastrophic hull failure. Only a handful showed small cracks, which inspectors caught and repaired using the same stress relief techniques before they spread. These ships returned swiftly to duty. The contrast with Liberty ships was total and devastating. The human arithmetic between Victory and Liberty ships was written in lives saved and missions completed. Across two vast oceans, in April 1945, the SS Wandafuka, a Victory ship, struck a mine near Okinawa. The explosion ripped a 20-foot gash beneath her waterline. The crew braced for the deadly chain reaction that had doomed Liberty ships, but the fracture halted cleanly at the first riveted crack arrestor seam. She limped into port under her own power, was repaired in 6 days, and resumed duty. A Liberty ship in a similar incident, the SS Richard Hovey, hit by a mine in February 1945, cracked lengthwise for over 90 feet, broke her keel and sank in 14 minutes, taking 37 sailors with her. The Pacific Campaign's entire logistics chain depended on the Victory ship's unshakable reliability. By mid-1944, as American forces surged toward the Philippines and Japan, every new offensive required millions of tons of cargo transported over thousands of miles of open ocean. Liberty ships could make the journey, but their fragile hulls meant lighter loads, slower speeds, and constant fear of mid-ocean failure. Victory ships ran fully loaded at 15 knots, 3 faster than the Liberty's 12, through typhoon zones without fear of splitting apart on a cold night. The statistics were staggering. From D-Day in June 1944 to VJ Day in August 1945, Victory ships hauled over 18 million tons of cargo with 0 structural losses. They operated in North Atlantic convoys where the water froze below 35 degrees Celsius. Conditions that had shattered dozens of Liberty ships. They sailed the Arctic supply routes to Murmansk, delivering critical Lend-Lease supplies to the Soviet Union in seas so cold that Liberty ships became brittle death traps. The SS Hobart Baker, a Victory ship, made 17 Murmansk runs without a single stress fracture. By comparison, the Liberty ship John Walker developed hull cracks on her second voyage and was retired from Arctic duty. For sailors, the psychological shift was profound. Oral histories collected after the war described the terror of serving on Liberty ships, vessels infamous for breaking apart without warning. Merchant mariners spoke of sleepless nights, listening for the ominous groan that might signal a fatal crack. Some refused to sail on ships known for previous fractures, but Victory ships restored confidence and morale. Crews trusted their hulls, pushed the vessels harder, and operated with boldness unthinkable a year earlier. That confidence translated to performance, faster port turnarounds, willingness to sail through storms, and steadiness under fire. At the Battle of Leyte Gulf in October 1944, 16 Victory ships supplied ammunition, aviation fuel, and materiel through kamikaze attacks and typhoon-force winds. The SS Kyle Johnson suffered near-miss bomb damage that buckled deck plates and cracked 3 frame sections. Yet she stayed in action, unloading cargo under fire for 4 days before heading for repairs. Her redundant structure and crack-arresting seams kept damage localized, preventing total failure. A Liberty ship under the same assault would have been abandoned as cracks raced uncontrollably through its hull. The economics were equally conclusive. A Liberty ship cost about $2 million to build. A Victory ship cost $2.6 million, roughly 30% more. But Liberty ships carried a 4.6% chance of catastrophic failure during service. According to 1944 data, disasters that claimed an average of 18 lives and destroyed cargo worth several times the ship's own cost. The Victory's 0 failure rate meant that the extra $600,000 construction cost paid for itself within 6 months, simply through eliminated risk and lower insurance premiums. By the war's end, merchant mariners had a grim saying that captured the truth. Liberty ships were built by the mile and cut off by the yard. Victory ships were built by the inch and measured by the year. Those inches, the careful weld sequences, the obsessive inspections, the engineered crack arresters, gave Victory ships decades of reliable service instead of desperate prayers every time the hull groaned in icy waters. Bessie Hamill returned quietly to civilian life in 1946. There were no medals, no hearings, no headlines, only a supervisor's modest letter of commendation. She never appeared before Congress, never saw her name printed in the technical papers that later celebrated the welding revolution she had sparked. The engineering establishment absorbed her discovery, translated it into equations and polished academic language, and published it as if it had always been theirs. The discoveries appeared to have come from laboratory research, not from a night shift welder's practical insight. For decades, welding textbooks taught stress relief sequencing without ever naming the woman who first recognized its necessity while watching hull plates twist beneath her torch. Yet her legacy runs through modern engineering, far beyond shipbuilding. Every welded structure today, from skyscrapers and bridges to pipelines and pressure vessels, follows sequencing protocols that descend directly from the procedures developed at Richmond Shipyard in 1944, the American Welding Society's 1947 structural code formally required center-outward welding sequences and post-weld stress relief as industry standards. Pipeline construction across Alaska in the 1970s adopted welding rules drawn straight from victory ship practices, preventing cold weather cracking in Arctic conditions. The Trans-Alaska Pipeline's 800-mile span of welded steel carrying hot oil through sub-zero temperatures exists because engineers applied the lessons Hamill revealed. Modern bridge engineering inherited those same principles. When the Point Pleasant Bridge collapsed in West Virginia in 1967, killing 46 people, investigators found residual welding stress as a contributing factor. Welds executed without proper sequencing had trapped stress within the structure. The resulting code revisions mandated the same sequencing and inspection protocols pioneered in the Victory program. Every welded bridge since then has incorporated them. During the Golden Gate Bridge's 1990s seismic retrofit, thousands of tons of reinforcement steel were added using computer-modeled weld sequences that minimized residual stress, an advanced echo of what Hamill had demonstrated with hand-welded plates in 1943. The offshore oil industry would learn that lesson, repeatedly and painfully. The Alexander Kielland platform disaster in Norway in 1980, which killed 123 workers, traced part of its failure to fatigue cracks from improperly sequenced welds. The Piper Alpha explosion in 1988, killing 167 men, began with a weld crack carrying residual stress. Each catastrophe sent investigators back to welding procedures, and each rediscovered principles proven 4 decades earlier on Victory ships. Today's offshore standards require stress relief heat treatment for all critical welds, directly mirroring the ovens Kaiser installed in Richmond's prefabrication sheds. Nuclear power pushed those lessons to their extreme. Reactor pressure vessels, containing immense heat and pressure, cannot allow even a microscopic crack. Welding sequences for these vessels are now planned with computational accuracy, simulating thermal and residual stress effects before a single weld is made. Afterward, the entire vessel undergoes post-weld heat treatment in massive furnaces, exactly as Victory ship sections did, to eliminate internal stress that could become a failure seed. Engineers designing those reactors in the 1950s explicitly cited Victory ship construction as their foundational case study. Hamill's insight changed not just techniques, but thinking itself. Before the Victory ships, design and construction existed in separate silos. Engineers designed, fabricators built, and neither side considered how sequence influenced performance. The wartime crisis proved that fabrication order mattered as much as material strength or geometry. Today's engineering education treats manufacturing process as inseparable from design itself. Students learn that even a flawless blueprint, executed with poor welding sequence, yields an inferior product compared to a modest design built correctly. The 5-day Victory ship timeline, while headline-worthy, was never the true miracle. Kaiser's yards could have continued producing Liberty ships at record speed, beautiful, deadly failures that looked seaworthy until they broke apart. The real triumph was the decision to slow down and do it right, to pause production and redesign methods around one welder's observation that defied accepted wisdom. That humility, to listen to a frontline worker, to admit that theory had missed what practice revealed, was the true revolution. Every modern manufacturing philosophy, from Six Sigma to lean production to total quality management, rests on that same foundation. The worker who sees what the engineer's equations overlook. Bessie Hamill died quietly in 1987 in Sacramento. Her obituary mentioned only that she had worked in wartime shipyards. No medals, no congressional testimony, no textbooks bearing her name. But every welded structure that stands today, every bridge spanning a river, every pipeline crossing frozen tundra, every pressure vessel containing dangerous energy, carries her legacy in its sequenced welds and relieved stresses. Silent proof of the welder who once asked why ships were breaking and refused to accept that that's just how it's done as an answer.